This is the second portion of the Chapter 5 video on alcohols, ethers, and thiols. In the last video, we looked at nomenclature and basic structure of alcohol, some of the characteristic physical properties. In this video, we're going to look at some of the characteristic reactions associated with alcohols. And so it should be fairly short, but full of goodness, I hope. The first thing that we need to talk about, or that is worth mentioning about alcohols, has to do with acidity. And they have a pKa, which is the negative log of the dissociation constant of an acid. I know that you all are familiar with pH, and you know that the pH is the negative log of the hydrogen ion concentration. Well, when we talk about acids, molecules that release hydrogen ions in solutions, we can look at the dissociation constant. We can calculate an equilibrium position for that, and the negative log of that is referred to as the pKa. It's not exactly the same thing as the pH, but it gives you an idea of the relative acidity of a compound. We'll talk a lot more about this when we talk about alcohols, or when we talk about acids, bases, and buffers second semester. But at any rate, alcohols, generally speaking, aliphatic alcohols, alcohols that are simple alkyl groups with OH groups attached, have pKa's of approximately 14, which makes them relatively the same kind of acidity as water. And as you know, water is not a very strong acid. It does have some, it does release some hydrogen ions on the order of 10 to the minus 7th, but not particularly acidic. Acid catalyzed dehydration is a very important reaction, and one that we're going to study in lab probably in a couple of weeks. If you look here, you can see the acid catalyzed dehydration of cyclohexanol to cyclohexene. This occurs in heat with an H2SO4 catalyst. This is a common way of building an alkene or making an alkene out of an alcohol. So if you look at the bottom of this slide, you'll see a situation where we're taking a tertiary alcohol and we're going to dehydrate it, and there are two possibilities. It can either dehydrate such that it will form the double bond on this side, or it could potentially dehydrate so it would form the double bond on this side. Now, which of those is going to predominate? Well, our rules tell us that when we have several possibilities, that the alkene with the greatest number of substituents will predominate. So if we dehydrate in this position to give us this first product here, we have no alkyl substituents on this side of the double bond, and we have two over here. So we have two substituents here, whereas if we dehydrate in this direction to give us this molecule here, we find that we have two substituents on the left side of the double bond and one substituent on the right side of the double bond. And so this would be the major product and this would be the minor product. Notice that when we lose the OH, we lose one of the hydrogens on the adjacent alkyl group. So the one with the greater number of substituents will predominate. Here's another example here where we have this substituted cyclohexanol with a methyl group on it. Again, we could dehydrate in such a way that it could dehydrate here in this position, or it could dehydrate here in this position. Again, the number with the most substituents, so try it out. When you dehydrate here, losing a hydrogen here in the OH to give us this double bond, and then the carbon on this structure, and I'll draw a little carbon into here, you can see that you've got 1, 2 substituents here, none here, and when we dehydrate into the ring, you can see that I have a cat that's trying to play with the pen, so hopefully he won't. And so you can take a look here. You've got a carbon, 1, 2 substituents on this side, 1 substituent here, 3 substituents gives us this as a major product. This is a minor product. It's important to recognize that the ease of dehydration is such that tertiary alcohols are easier to dehydrate than secondary than primary. And so the next example that I give you asks you to take a look at this problem where you have a dehydration of 2-methylcyclohexanol forming compound C and water, and then going from there to compound D. And it asks you what are the 2 possible structures that could be produced from that. So if you take a look at 2-methylcyclohexanol here, you can see that dehydration is either going to occur here or it's going to occur here. If we look at this first one, we see that the OH comes off of this carbon and a hydrogen comes off of this carbon, remembering that that doesn't show because of the cyclostructure. So here we've got a situation where we've got 1, 2, 3 substituents. This could also form this second structure over here, but this would be the major one. And when we react that structure, compound C here, with water and H2SO4, this should be screaming at you, Markovnikov addition. So you've got a hydrogen here, you've got no hydrogens here, so the hydrogen would come on here, the OH would come on here, and so basically we've effectively moved the OH group from this carbon to this carbon down here. So basically we've been able to kind of in a two-step synthesis move the carbon from one, or move the OH from one to another. We've been able to take a secondary alcohol and make it into a tertiary alcohol. Kind of a clever little synthesis there. Another of the really important reactions of alcohols has to do with oxidation to aldehydes, ketones, and carboxylic acids. And this, again, is another pretty important kind of reaction. It depends on the degree of the alcohol. Primary alcohols, if you take a look at them in this first line, oxidize quite readily using permanganate or potassium dichromate in the presence of an acid catalyst to form aldehydes. This is oxidation because we have lost a hydrogen and we've gained a double bond on this oxygen. And remember, a couple weeks ago we talked about that in class. So it's important to recognize that when we're talking about oxidation or reduction, we're looking at gaining oxygens or losing hydrogens, and in the course of course in reduction we're gaining hydrogens and losing oxygens. So just kind of something to keep in mind, because I'm going to throw around that word oxidation a lot, and I don't want you to think that you need to calculate oxidation number or be counting electrons. It's not necessary for our purposes. So we readily are able to oxidize primary alcohols to aldehydes. The difficulty with this reaction is that rarely are you able to simply get the aldehyde unless you're very, very careful about your reaction conditions. Usually there's adequate reagent available in the form of dichromate or permanganate to further oxidize the aldehyde to a carboxylic acid. And so frequently you will see in reality that primary alcohols will oxidize and their final product will be a carboxylic acid. In the case of secondary alcohols that we have down here, we are going to oxidize in such a way that we lose the hydrogens here, and we're going to gain a double bond and form a ketone. So ketones are the product of secondary alcohol oxidation. And in the case of tertiary alcohols, we have no reaction because there are no hydrogens that can be lost on the OH bearing carbon, and so we can't form this carbonyl group, and remembering this is a carbonyl, so we can't form carbonyl groups because the primary alcohol, the carbons are all attached to other alkyl groups, so there would be no reaction of a tertiary alcohol in conditions of using dichromate or permanganate. So this last problem in this video asks you to show the products of oxidation with dichromate of cyclohexanol, and cyclohexanol, showing you here, we'll lose a hydrogen here and it'll lose a hydrogen here to form this ketone, which actually is called cyclohexanone. You don't need to know that. We haven't got to ketones yet, but you can at least draw the structure. And in the case of 2-pentanol, we have CH3, CHOH, I lost a bond there, CH2, CH2, CH3. So we've got 2-pentanone. This is going to, secondary alcohol, it's going to become a ketone, so we lose the hydrogen here, we lose the hydrogen here, form a double bond, and we get that ketone, which happens to be 2-pentanone, but again, it's not necessary that you know that at this point. This completes the group of reactions that we're going to talk about in this chapter, but do bear in mind when we talk about the formation of alkenes from dehydration of cyclohexanol, then all the reactions that take place with alkenes are possible from those starting materials. So we can start with an alcohol, make it into an alkene. We can then do all kinds of Markovnikov addition. We can do cleavage. We can further oxidize the alkene. In this case, we can oxidize the alcohol and then continue to react it in other ways. So this is a little bit for you to chew on. We're starting to build our repertoire of reactions and reaction types. Be sure that you're keeping your alcohol or your reaction sheet up to date. You're going to be needing it more and more as we go along. There will be one more video that goes along with this chapter that's going to deal with thiols and ethers, and that will be coming to you soon. I'll see you in class.